Now, we just go on with the last possibility for concrete beams I want to show today, and that is to build the bridge beam on scaffolding, not in free cantilevering, in the final position, no turning in, but on scaffolding. Again, two possibilities. One possibility is just to build a long scaffolding underneath the bridge. That may be the case if we cross a valley, like in this Leven River Bridge in Scotland. There's a little Leven River, it's more a creek than a river, I would say, and all this is a valley, but not too deep. I think it was 10-12 meters. And we had assumed that the contractor would use maybe incremental launching or so. No, he said for him the most economic was to build a scaffolding all the way as we see it here, cast the beam on top, and then, so to say, by stressing the cables, lift the beam out of the scaffolding. A similar use with stationary formwork was done for a very much bigger bridge, the longest, or the second longest, 1,008 meters, stone cutter in Hong Kong. And there it was rather high up, 40 meters. In my field, not a very economic way to build a bridge, but that's what the contractor decided. We see here spans of 70 meters and height in the same range, 60, 70 meters. Two separate cross sections, concrete for the side span, steel for the main span, connected with substantial box cross girders. So if we cut through a cross girder, 3 per span, it looks like this, and in between we have the two separate. And here we see the building up of the scaffolding with auxiliary piers in between the final ones. And I tell you, I was on site several times. It wasn't our design. I always felt for what you put into the scaffolding here, temporary, you could build a rather substantial bridge. I thought it's not very economic, but they've done it. And here then we have, in the next stage, we have the formwork installed, and here finally we have cast the beam on that stationary scaffolding. Now, another possibility here we show for the Flehe Bridge across the Rhine River, 1975-76. I was project engineer for this concrete back part, 780 meters long, a rather substantial bridge, where the backstays, the steel cable stayed bridge in the span, were anchored. Now, all these spans were built span-wise, 60 meter long, on a self-launching form. So after the contractor didn't put the formwork underneath the whole 780 meters, it would be too expensive, but he used always 70 meters and then moved forward the forms, the scaffolding for the next 70 meters on a self-launching formwork. Of course, auxiliary piers in between the 60 meters. A view back from the tower. We see here the major part is already built, and we are now approaching near the tower the region where the stay cables are anchored. And this is a look into the forms. We see here the A tower, very small in behind. It's the Rhine River near Düsseldorf. And we see here the stay cable, the steel pipes for the anchorage of the stay cables inside the form. These were, in general, the possibilities we have for building cable-stayed concrete beams, classically main spans and free cantilevering, precast or cast in place. But we can also use a rotating in the bridge, and we can, especially for the approach bridges, use some sort of launching incremental or span-wise, and that about shows the ways we have. Now we come to the steel beam. Again, in general, we have similar methods. Naturally, the king of building steel bridges, even more than in concrete, is free cantilevering, but we also have possibilities of launching and some other shifting. Now, stonecutter bridge. I just showed you the building of the concrete approaches on a stationary form, 60 meters high, rather involved. Now, we have now for the stonecutter bridge here reached the concrete approach beam near the tower, and now we start with building the steel beam. It is unusual for the stonecutter bridge that the steel beam extends into the side span where the concrete is. Normally, the concrete extends out here because from material this is less expensive. However, you may need an additional construction method for that part of concrete, like I'll show you for the Normandy Bridge. So in this case, they used more expensive steel material to extend here, but they could use in principle the same construction method for the steel beam they used for the main spans. So a cut-off, more material cost, but savings in construction method. Always the dilemma we have to consider during construction, the two. And in this case, they voted for the steel beam to extend into the approach span. So the steel goes until here somewhere, lifted up, it's a twin beam, and then from here onwards it's the regular free cantilevering, lifting of the last beam element, again second in record, 1,008 meters. We will see soon the world record holder. Now, nearly at the same time, a little bit later started, but a little bit earlier completed. So the world record never went to finally to the stonecutter bridge, but went to Sutong across the, I think it's the Huanghe, the Yellow River in China. 1,088 meters, nearly done, view from the tower. Transportation of the last element by barge, lifting of the last element, and then of course the installation of the last element is always a little tricky. It's normally precisely then measured, the distance, and very often the last piece is fabricated too long to be able to cut it off a little bit exactly to where you land. I mean, after 500 meters each side, you can't really normally foretell it's on the millimeter. But in addition, what you have to do is you have to spread the two beams which are already erected in order to be able to lift in, to thread in the last element. So this temporary scaffold beam here, truss girder, is used to spread the two halves, which of course at their fixed points must provide the possibility for 10 centimeter sliding. Open up, thread in, lift in the last element, and then come back. And you've measured all that extremely carefully at night without temperature, and then the two should fit very closely so that you can weld around. That's the same with all the final centerpieces of steel cable-stayed bridges. Now, this typical method for steel beams, one could go on and on. Most steel bridges have been built this way. It's rather straightforward and simple. Also, we can launch steel beams. The most famous example for that is the Millau Bridge in the south of France, where the whole, 2,500 meter, you see it here disappearing in the fog, is put together here in the fabrication and shifted with the final tip or tower here at the tip to support the cantilever. We will have a whole half lecture on the Millau Bridge later, so that's why I just give you the example, launch the bridge in. As an exception, transverse shifting, which is also a sort of launching, not longitudinally but transverse, has been used for the Rhine River Bridge. The situation in Düsseldorf was, it's the Oberkassel Bridge, Düsseldorf-Oberkassel is a part of Düsseldorf. There was the temporary wiring for 20 or 30 years, but originally it was done temporary in the after Second World War, over here. And this is such an important inner city arteria that you couldn't just tear it down and then for a year or two close it to build the new bridge. So what was done? The old bridge was left in use. The new bridge was built alongside. The traffic was temporarily transferred to the new bridge. Then, while the traffic runs here, the old bridge was dismantled, and the pier then, the main piers were extended. You couldn't use the old ones there. And finally, during a closure, more or less the weekend, a few days more, the bridge was closed and the new bridge was shifted over, I think 47 meters, in the new position. Now we see here where the tower sits, we see here the bridge, and we see here the way it has to be moved transversely by 47.5 meters. How to do that with a cable-stayed bridge? Well, there was this design which is particularly suited to transverse shifting. Single tower, symmetric in length, left and right. And for shifting, these cables were shortened, I say, was pulled at, that all the load was removed from these piers, centered on the tower, about 10,000 tons. And so the bridge was only supported then at that time here, 10,000 tons, and a little bit for balancing at the two abutments. And so then it was more or less on this one piece, on this one point, shifted transversely with, on a, at that time, the biggest neopod bearing, 3 meter diameter for 10,000 tons. Again, on a sliding surface of PTFE, Teflon on one side, and polished steel. The sliding track was polished steel, and underneath the bearing was the Teflon. So the thing was shifted over, and there were two sets of jacks. One jack always was pulling, the other with a center hole pull rod here, and there was the move, back, move, back, move, back. So in about, I think, 2 days or so, the whole bridge was shifted. One of the biggest shifts, 10,000 tons to date. So much for the steel beam. And now we come to the third type. We have the composite beam. And you remember a composite beam has a steel girder grid underneath and a concrete roadway on top. So the main possibilities or main differences, first of all, in composite beam construction is, do you have precast elements, again, as we know from the concrete beams, precast elements for the roadway slab, or do you do the thing cast in place? And normally you construct that separately, but there's a third possibility that you install the complete beam steel plus concrete. That's what it is, basically. Now, let's look at it. We use the example for composite with precast slabs, the Houston Ship Channel crossing at Baytown, which I did in the early 80s. We will also have a full lecture on that. There are all sorts of interesting things. But in this particular case, we see here we lift the steel grid pieces, 12-meter cable distance, so they are 12 meters long, and each beam about 25 meters wide. Here are the main girders, the cross girders, a spreader beam, and here you can barely see it. The Houston Ship Channel goes to the Gulf of Mexico, and here's a ship which runs through. So, transport on water lifted up about 60 tons. Now that's a difference to the 300 tons we have in concrete, or the steel deck, orthotropic deck weighs about 200 kilo per square meters, 180. You can't do it less. And if we calculate 12 by 20 is about, you come to about 60 tons more. So a complete steel beam, which we have seen until then, has about 100, 120 tons, about 400 or 500 kilo square meter. And here we have only 60 tons. So a distinct advantage of composite construction is that you have the smallest weights you can have for the new beam section to lift up. An important advantage for cost of lifting equipment and the load on the beam. Then, after we've installed the steel, we then lift up, in this case, precast elements, 20 tons a slab, a concrete slab, also nearly peanuts for major bridge construction. So, small weights to lift, the main advantage of composite construction. Of course, we have the problem with precast element joints. The advantage of the precast elements is, again, casting under controlled conditions, low shrinkage and creep when built in, because they are about a year old. Shrinkage and creep values are strongly reduced. But the disadvantage is, how do we close the joints? And we have used here for Baytown, I think, a rather reasonable solution. First of all, we want to support the precast elements on the top flanges of the cross girders. We don't want any auxiliary supports, place them where they are finally. That means we have here something only like 20 centimeters distance. With that we can use loops, Schlaufenverankerung, loops for anchoring for connecting the rebar. However, if we take the loops all the way, experience shows that there tend to be concentrated rather big cracks, which we want to avoid on the top. On the bottom we don't care so much, and anyway there's a compression. So that's when we said, okay, the top, we widen this distance, we put in a slot into the concrete deck long enough to have straight lap splices, which are known to distribute the cracks, if there are any, finer over a wider distance. So that's why we have this two-part joint. On top, straight lap splice for crack control. On the bottom, we need to support on top of the flanges and thus have to use loop anchorages. I think it's still very reasonable. Of course, we have from the cable inclinations the beam under compression. That helps a lot that we, under permanent load, these joints are under compression. We see here a picture, the shear studs coming through, the lap splice and the loops in the bottom. Then, of course, we have the casting with a special low shrink. It's not a grout, it's a concrete. There is gravel in, has the same strength as the others, and it's what we call plasticized. So it can take a little more tension. It's a very special concrete, low shrink, can take tensile stress. And it worked very well. We didn't have problems. Baytown was opened early 90s, so it's nearly 20 years old. No problem with the joints. For the Yangpu Bridge in Shanghai, where I was checking engineer for the World Bank in the early 90s, it's a composite beam. It was world record at that time, 602 meter main span. And they used a little trick there, which I think is unique. We said we have compression in the roadway slab in longitudinal direction from the inclined cables. Now, in transverse direction, the roadway slab acts as a top flange of a simply supported girder between the cable anchorages, and the top flange, of course, from a positive moment is under compression. But they said in Hong Kong, okay, they had here a rather wide, an important joint in the center of the bridge running longitudinally, and they said, we'd rather have a little bit more compression there. Now, you don't do that with post-tensioning, not in a composite beam. That's uneconomic. The post-tensioning runs into the steel, no good. But we do something else. Before we place the precast elements and cast the center joint, we artificially lift up, push up the beam to install a positive moment or a hogging curvature. Then place the elements, cast the joint, and when the joint is hardened, we take out this auxiliary underneath. So then we have, in addition to the simply supported beam, those moments in the joint, meaning the compression from that moment, which results from this artificial supporting. Here we see it on site, the front piece, steel grid, cross girders, and here we have these air struts artificially pushing up the deck in transverse direction. So that was a precast deck, and now we come to the same possibility, to the alternate cast in place. What we had for the complete beam, we can do it precast or cast in place. We have the same just for the roadway slab of a composite girder, precast or cast in place. The advantage of cast in place is that we do not have the joint problem, and we do not have to transport any precast elements, although the low weight and good possibilities for the joint do not make the advantage of cast in place very big. It more or less depends on what the contractor likes and what the design use in the country is. But both, in my opinion, are more or less equal. We use the example of the Niederwartha Bridge, a few kilometers away from here. Transportation of the steel grid sections on the Elbe River to the side, lifting it up, aligning it to the already installed beam, and then welding. And then comes the roadway slab. First of all, we have to place the formwork on top of the cross girders. As we say here, we see here the cross girders themselves with shear studs protruding for shear connection. Then we place the reinforcement, we cast the concrete, and use some extended machinery to plane it to have a very smooth surface. Very standard and very understandable. I don't have to go into that anymore. Now, there is the possibility of installing the complete beam, meaning steel grid plus concrete on top. That makes, you can use a cast-in-place fabrication on shore. However, you have to lift bigger elements. That's the disadvantage, and you still have the joint to close. We see here the protruding reinforcement, same here. So we still have the cast-in-place joint, which hinders the progress of construction. So it takes away part of the advantage of composite construction by installing small weights, steel grid, and deck slabs separately, without overcoming the main disadvantage of precast, that we have a joint. So it's rarely used. The only typical example I know is the Rion-Antirion Bridge, and there they had quite other problems besides how to do the joint. We will have a lecture on that, especially with earthquake and all these things. And so it's of course a very fast construction method, and they had very heavy floating equipment there anyway, which could lift the whole thing, didn't cost them anything. So that's why they used the complete cross-section. There. Another case for a complete cross-section is the Kap Shui Mun Bridge, Hong Kong to Lantau Island. I mentioned that already. The approach bridges were incrementally launched. Now, this is a double-deck cross-section. We have 6 lanes of freeway traffic on top, and we have rapid transit public transportation here on the bottom. And in addition, we have emergency lanes in case one of the rather frequently occurring typhoons in Hong Kong blows, then we can't use the top surface. The typhoon would blow the cars away. But we have the airport, which is a major piece of infrastructure, and we need emergency vehicles and so on running. So during a typhoon, they can run inside instead of the public railway here. That is why there is a 2-story cross-section. And we did quite an unusual thing. We made this composite, and we won the competition, our contractor there, by using steel frames and steel webs, but top and bottom concrete roadway slabs. So it's a composite cross-section, unusual, but anyway it is. And for construction, this thing was about 8.5 meters high. That's what a double stock cross-section comes to, 8 meters, something like that. But we had a regular cable distance. So again, we came with 8 meter beam depth, you can cantilever every section without tying back your lifting equipment. And so in this case, it was decided quite properly to install the complete elements with the concrete cast already in place, top and bottom, weight of 500 tons, one of the heaviest pieces ever lifted, and just here a beam supported 2 cables back and here with a hydraulic jacks putting up, but because the big height, the beam could take the bending moment from lifting and installing these 500 tons before the cable was in. And that's why for this particular location, with the great depth of cross-section, it was a good method and an efficient method to use the complete cross-section because it didn't cost anything but saved steps on site. Now, finally, we can also launch a composite beam. Example, Heinola Bridge, Tätiniemi, as they call it in Finnish, but I thought we'd rather go with Heinola, that's a little easier. Now we see here 3/4 at least of this bridge are, so to say, approach bridges, continuous girders. And the cable-stayed bridge is a fairly small part of the total cost. And whenever we have this situation, we must find the most economic method to build the vast majority of the bridge, meaning the approaches, and then try in some way to use this method also in the cable-stayed area. And not say, okay, we build the cable-stayed bridge, that's the interesting one, and the others will look after themselves. No. You must optimize the construction method where the bulk of the bridge is. If you, as normally, have a large cable-stayed bridge and small approaches, okay, then you go for the cable-stayed bridge and somehow do the approach. If you have a very long approach, you find the best way for the approach and somehow try to fit in the cable-stayed bridge with the same method. And that was done here by saying, okay, we launch the steel girder across the whole length of the bridge. That's the steel girder. We have here the launching nose. And what we do is we place 2 auxiliary piers here. So first of all, we build the complete bridge, including cable-stayed part, with auxiliary piers. And then we install the cables and take the auxiliary piers away. That's the proper way for the approaches, and by using auxiliary piers, we can also apply it for the cable-stayed bridge, and so in total, this gives the minimum cost as compared with 2 construction methods by saying, okay, a cable-stayed bridge, we know, we don't have to think, that's free cantilevering, and here we, whatever may be launching. 2 separate construction methods always cost additional money. So we'd rather have one continuous method through and then do what is necessary to adjust it to the cable-stayed bridge. That's something you should remember. Where's the bulk of the cost? That's where we go for, and then try to squeeze in the smaller part. So, incremental launching of the whole bridge. We see here the towers are only being constructed while this is launched, and we can see here in the region where later on the stays are, we can see some auxiliary piers, and they are here behind. So first of all, we have the continuous bridge, partly on auxiliary piers, And then we build the cable-stayed bridge. And first of all, we cast the roadway slab still on auxiliary piers. And once the roadway slab is cast, then we install the stay cables. Well, this was an overview over construction methods for tower and beams of cable-stayed bridges. As mentioned, stay cables are a large variety. That's an extra lecture. And let me just repeat briefly, thinking back what we've discussed today, what we were looking at. We looked first at towers. Steel towers, we build piecewise prefabricated steel pieces. We lift in with a crane, either a floating crane or tower crane, and then once it's in and aligned, it's welded, and that's it. Fairly simple. Now, concrete towers, we nearly always build cast in place. We do the building by free cantilevering, say, and there we have the two possibilities of sliding forms and jumping forms. I told you I prefer the jumping forms for safety, may be a little bit more expensive, but once you're in the first discussions with the contractor, try to steer him a little bit into the way of jumping forms. Sometimes you succeed, sometimes not, and if it doesn't work out, then you later have to change all the drawings. So go for the jumping forms. And if we have A towers where we have the two tower legs inclined, creating moments to the inside which may be bigger than in the final stage during construction, we use 1, 2, 3, whatever is required, auxiliary struts to take up the moments from the inclination. That's basically all there is to tower construction. Now, for the beam construction, we first have to distinguish in our mind, as always, we have concrete, steel, composite material, which is on one hand distinctly different in the construction method. On the other hand, naturally, there are similarities just on another level. So when we start of thinking of beam construction, first of all, the overriding method for all types is free cantilevering. That's a big advantage of cable-stayed bridges because the intermediate systems are stable. We have the same flow of forces in the intermediate stages as in the final stage. That's one of the big advantages of cable-stayed bridges. So, concrete, free cantilevering, two possibilities, cast in place or precast. Advantage of precast is good quality of the elements, may be rapid progress during construction. The difficulty is the high lifting weights in the range of 300 tons, which either loads the beam heavily, or if we have a floating crane, we need a rather big crane, which costs more money per day to rent than a smaller crane. We have to cater with the joints. Precast elements, we can either use match cast, glued, the simplest, the fastest, pioneered by the French, but we did it, for example, for the Pesco Bridge. Or we use cast-in-place joints. Takes some time because we need to form, we need to reinforce, we need to cast the concrete, and the worst one, we need to wait until the concrete is hardened. So that is a disadvantage. On the other hand, if we used cast in place, cross sections, we have the problem normally of supporting the new piece of cast-in-place concrete at the tip, because we have the length of cable distance, 10, 12 meters. Very often only 1.5, 1.2 meter depths. So the beam can't take the negative cantilever moments. So auxiliary staying of the form traveler, time consuming by elongating, and of course material consuming for the stays. Then next step, we use the final stay cables for supporting the form traveler, which is a very reasonable method. Or we have a beam so deep that it can take the cantilever moments. I showed you the second Panama Canal, where we had a 4.5 meter deep beam with only 6 meters cable distance. So to cantilever 6 meters with a depth of 4.5 meters, you don't need any auxiliary support. Of course, there are some disadvantages with such a deep beam. That's why I said it wasn't our design, but the advantage was during construction. Then finally we come to the composite beam. There we generally install the steel girder grid separate from the roadway slab. We come to weights, little weights of about 60 tons, which is very reasonable. The roadway slab can be precast or cast in place with the same advantages or disadvantages as we have mentioned before. And in addition, there are special methods like launching and rotating. Well, I think that sums it up fairly. Thank you very much.